Hello everyone, welcome to the presentation Bringing Reset Domains and Power Domains Together. Set reset flops augmenting complexities in power-aware RDC verification, which is called Reset Domain Crossing Verification. My name is Manjunatha and I am Application Engineer for Design and Verification Technology Products at Siemens EDA. In this paper, we have presented some RDC cases in which the designer might miss some key reset assertion problems involving priority flops, which may lead to corner case situations that are difficult to find out, debug, and analyze. We worked with a very acquainted design engineer, Inayat Ali from NXP Semiconductors, and our colleagues Moyeen Abdul and Manish Bhati from Siemens EDA. They helped us share their valuable thoughts on priority flop design, reset related issues, and its challenges. Bringing reset domains and power domains together tends to increase the reset signaling problems that results in functional and metastability design issues. When data from one asynchronous reset domain propagates to either a different asynchronous or synchronous or no reset destination domain, the reset domain crossing path issues are inevitable. This problem becomes complex when RTL is instrumented with UPF elements, as they are prone to erupt and devise multi-reset related issues due to addition of extra logic in your design. Along with conventional simple resetable flops, the set reset flops with multiple set reset asynchronous domains increases the reset assertion issues many folds. This is where verifying the interaction between reset domains and power domains, along with the set reset flops augmenting the complexities, become a challenging task to the designers. Let us now understand the reset domain crossing problem in a design. In a sequential design, if the source flop R1 makes an asynchronous transition to a reset state, it can cause a transition inside the setup and hold window of the destination flop R2, and it can lead to a metastability issue. These RDC problems can occur between both synchronous and asynchronous clock domains as well. The waveform analysis shows the assertion of RST1 creates an untimed path from R1 register to R2 register, which can cause metastability when RST1 reset is asserted and RST2 reset of R2 register is deasserted. In this slide, we present some of the basic RDC structures that will help understand the complex cases of RDC paths, which we will be discussing in the upcoming slides. We will use these basic RDC structures to correlate and interpret how complicated the RDC paths can become during the utilization of set reset flops in the UPF instrumented RTL when compared to a simple resettable flops. Different color codes in the schematics indicate that the registers are in different reset domains. Figure 1 depicts a simple resettable flop RDC structure in a non-UPF RTL with two asynchronous resets, active low asynchronous resets, TX_RST and RX_RST. Figure 2 depicts a simple resettable flop RDC structure in a UPF instrumented RTL. In this scenario, we can see that how UPF logic added breaks the previously synchronized crossing by adding a combinational logic before the 2DFF synchronizer. The design now without UPF instrumentation has become a little more complicated by replacing the simple resettable sequential element by a set reset flop structure. The RDC structure with SR flop in a non-UPF RTL with source register being controlled by two signals TX underscore RST and TX underscore set, where TX underscore RST is an asynchronous reset which is treated as a priority reset based on the if-else condition in the always block, and the TX underscore set is an asynchronous set signal. The destination register is now controlled by the RX underscore RST asynchronous reset signal. In this case, based on the relationship between the reset pairs TX underscore set and TX underscore RST, the RDC problem at destination flop can be determined. An important factor to note here is the number of resets has increased when compared to the simple resetable flop structures, which increases the probability of RDC problems and complexity of designers' analysis effort. Let us now further complicate the set reset flop RDC structures by inserting UPF logic to the RTL and study the impact of RDC analysis. The source flop is controlled by an asynchronous set reset signals TX underscore RST and TX underscore set present in the source power domain PD underscore source. The destination flop is controlled by asynchronous reset RX underscore RST, which is present in the destination power domain PD underscore destination. The low power element added to the RTL is controlled by power control logic, which consists of signals driven by a different asynchronous reset domain RST underscore power. In this scenario, we are now dealing with multiple resets in 4 different asynchronous reset domains, that is TX underscore set, TX underscore RST, RX underscore RST, and RST underscore power. Here, we are not just looking at the 4 different reset domains, but also we need to consider the impact of 2 different power domains, which brings in the necessity of concurrent multi-domain verification. Until now, we have just seen simple, straightforward scenarios involving set-reset RDC structures in low-power RTL. Similarly, we may have many such cases with corner situations in the design, and verifying such RDC paths can be painful for the designers when dealing with huge SOCs and IPs, where reset sequence and its relationship between these multiple resets in multiple power domains should be accounted for. In this paper, we have studied and explored the potential RDC problems with set reset flops in the power-aware RTL. Listing below are some of the few important priority set reset flop structure cases closely studied that can lead to new RDC problems. Let us discuss this case by case in detail in the coming slides. Please note the color coding in the schematic indicates different power domains for the block instances in the design. The U underscore F1 is a priority flop. The notations AL and AD, which means asynchronous load and asynchronous data, indicated for the pins of U underscore F1 register is the synthesis output structure for the set reset priority flop. Pins AL and AD are active based on the values of reset and set. U underscore F1 flop will either be in reset or set state when AL pin is active and will be in functional state when AL pin is inactive. And the AD pin determines to drive either constant 1 or 0 based on the reset and set values. Case 1, RDC paths formed due to insertion of isolation cell along the data path. Without insertion of isolation cell, RDC path crossing exists between source register U_F1 and U_F2 register. The TX register is a set reset register which has RST1 and set1 active low asynchronous reset, and the RX register has RST2 asynchronous reset domain. Asynchronous assertion of either RST1 or set1 at U_F1 can cause metastability at the flop U_F2 instance when RST2 is released. That is, when U_F2 is in a functional state. With the insertion of isolation cell along the data path between U_F1 and U_F2, we have a new asynchronous reset domain, RST3, driven through the register U_F3, driving the isolation enable of the UPF cell. This will result in a new RDC path during the data transfer mode or in an isolation mode. The data transfer mode is when both the source register U_F1 and destination register U_F2 power domains are turned on. And the isolation mode is when the source U_F1 register is off and destination register U_F2 is turned on. That is, when RST3 reset asserts asynchronously while RST2 is in the deassertion state. Case 2. Insertion of isolation cell creating an inference of multiple reset domains. Before UPF instrumentation of isolation cell along the reset path, the RDC crossing exists between flops U_F3 with RST2 reset domain and U_F1 driven by set reset register F2 instance with set1 and RST1 asynchronous reset domains. Let us assume to mark this particular RDC path as a safe crossing, the user has correctly specified reset assertion order between RST1, set1 and RST2 reset domains. But with the insertion of isolation cell along the reset path for U_F1 flop, the tool infers multiple reset domains at the isolation cell output. This makes crossing unsafe as now there is an RDC path formed between U_F3, which is in RST2 reset domain, and U_F1, which is driven by multiple reset domains that is contributed due to RST1, set1 and RST3 reset domains. This will result in disruption of reset assertion order that was specified earlier between RST1, set1 and RST2 reset pairs. Case 3. Isolation cell disrupts RDC paths controlled by data isolation strategy. Data isolation strategy is a special technique to control or synchronize the safe data transfer between two reset domains where data control signal blocks the data transfer when TX signal changes in the metastability window. Without UPF isolation cell, the RDC crossing between F2 set reset flop and U_F2 flop, which is in RST3 reset domain, is controlled by data isolation signal data_control. The data_control signal isolates the output of F2 flop when either of the F2 flop resets set1 or RST1 asserts asynchronously, thus avoiding asynchronous data change from causing metastability at the RX flop U_F2. With the insertion of isolation cell, the isolation enable is now driven by a new reset domain RST2, adds a new RDC path between U underscore F1 and U underscore F2 registers, hence disrupting the safe RDC paths which was earlier controlled by data isolation strategy. Case 4, isolation cell disrupts reset assertion order sequence specified during the non-UPF RTL analysis. Without UPF instrumentation, the crossing exists between U underscore F3 flop operating in RST2 reset domain and F2 set reset flop controlled by RST1 set 1 reset domains is a safe crossing because the reset assertion order defined between RST1 and RST2 reset domains was enough to avoid metastability propagation at F2 flop. Consider a situation where source power domain of U underscore F1 instance is turned off in the design. This will result in the clamp value constant 1 disabling the reset RST1 of F2 set reset flop. This further breaks the existing reset ordering and thus creates a need to define a new set of reset assertion order sequence for reset groups RST2 and set 1 reset domains to avoid metastability propagation at F2 flop when RST2 reset asserts asynchronously in the design. Case 5, isolation enabled signal driven by internally generated resets affecting the non-RDC path. Without UPF instrumentation, it looks like there is no RDC crossing between the TX flop U underscore F2 and RX flop U underscore F4, both being operated in set 1 and RST1 reset domains. Even with UPF instrumentation of isolation cell, it doesn't seem that it will affect the RDC path as the isolation enabled signal U underscore F5 register seems to be driven by RST1 reset domain from reset synchronizer sources U underscore F3 sync 2 and U underscore F3 sync 1. One key observation to be noted here is that the RST1's deassertion is synchronized from CLK1 clock domain to CLK2 clock domain. And note that the output of NAND gate will make the deassertion of RST1 as an assertion for U underscore F5 register. Since U underscore F5 register is in clock 1 domain, output of NAND gate will act as a new reset as the assertion of output signal of NAND gate is asynchronous to CLK1 clock domain. We will treat this signal as a new reset and term it INT underscore RST as it is an internally generated reset. This new reset will fall into a new reset domain and will create an additional RDC path between U underscore F5 register and U underscore F4 register. Proposed new rule check sets. When a design is implemented with the notion of power intent specification through the UPF artifacts, we need to ensure the original RTL functional behavior and its architecture is not impacted or disturbed by the additional power control logic. As a part of this, we have observed it is important to define some new rule checks, and some of them are derived from a previous DVCon paper on simple resettable registers. These rule checks help designers verify statically the reset propagation and integrity. Check 1, asynchronous reset set signal of SR set reset flop driven by power off domain. The asynchronous active low reset signal RST for F2 set reset register is driven by source power domain U underscore F1 flop. When the design is operating in sleep or standby mode, the power control configuration could turn off the power domain for U_F1 instance. With power states defined for standby mode, the reset pin of F2 flop reads the clamp value constant 1, which deactivates the reset RST as it is active low reset. Hence, the set reset flop F2 output in power saving or standby mode can be associated with set 1 asynchronous active low reset domain. This check helps designers to ensure that all the registers are reset and no register is left out because of resets originating from the power off domains. This ensures the correct state of design during the reset. Check 2. Asynchronous reset set signal driven by isolation logic is always active due to its clamp value. When the source power domain of U_F1 flop, which is in RST1 domain, driving the asynchronous reset pin of F2 flop is isolated or powered down, the asynchronous active low reset signal of F2 flop will be driven by isolation cell clamp value constant 0. This prevents the F2 flop from getting out of its reset state. The set 1 reset domain will no longer have any impact on the F2 flop during the power down state. This check ensures users to verify whether the asynchronous reset signal, which is driven by a logic that is a constant value, prevents the resettable element from being released from the always active reset state or not. Check 3. Isolation enable is driven by a different reset group. We can see that the low power elements like the isolation cell enable signal is being driven by a different reset groups, RST1 and set1 reset domains. Power control logic isolation enable can be driven by a simple resettable flop or a priority flop. In the case of priority flop driving the isolation enable, it can lead to an additional RDC paths in the design as previously discussed in the case 1 scenario. To resolve this, we need to define the correct reset groups for the isolation signal such that it belongs to the TX or RX reset domains. This check ensures that the designers resolve the increase in the new inferred resets, inferred due to combinational logic expression of RST1, set1 and RST2 reset domains due to insertion of isolation cell. In summary, this paper is part of our effort to bring out the new trending technology that deals with the low power designs to understand how the set reset functionality impacts the design. We have explored the new evading metastability functional issues arising due to complex set reset flop structures in the UPF RTL designs. The challenges dealing with how the set reset priority flop structures increases the complexity of new multiple inferred resets, leading to rise in the RDC paths. The need for concurrent multi-domain verification of the reset clock and power domains together is inevitable in the design flow. We have also proposed to enhance the new rule check sets for the UPF instrumented designs having priority set reset flops to ensure the correct reset architecture and the connectivity.
Hi, good morning, everybody. This is Roger. As you probably have noticed, Manju was a bit late, so that's why we played his video. But I see now, Manju, you're online, so we still have a few minutes left for questions if you have any. So please use the chat box, the chat window to enter your questions if you have any questions.
Yeah, thanks.
So sorry about that. I was late. Yeah, I'm going to answer any questions or any comments on the paper.
Okay, if there are no further questions, I want to thank Manju for his presentation, or his view in this case, but that's not a problem. It was quite nice to see it. And then let me start by introducing the next speaker, who is Aditya, who is a graduate in electronics and engineering from the Delhi Technological University, and he's currently working for Samsung for over 2 years now. His main research interest is in the domain of digital design and verification, as well as low power VLSI design. And the presentation is about, the title of his presentation is a methodology for evaluating silicon artifacts in a DDR4 3DS PHY by using channel modeling. Again, if you have any questions during the presentation, please feel free to enter your questions in the chat box. And of course, don't forget to vote for the best paper award. Aditya, the floor is yours.
Hi, Roger. Are you able to hear me?
Yes, Aditya, I can hear you.
Yeah, thank you for the introduction. I'm sharing my screen. Is it visible?
Yes, it's visible.
Yeah, just a moment.
Sure.
Yeah. Hello, everyone. Welcome to DVCon Europe 2021. My name is Aditya Kumar, and I would be presenting my paper titled "A Methodology for Evaluating SI Artifacts in DDR4 Series 5 Using Channel Modeling." We will start the presentation by understanding the changing landscape in the VLSI design industry and the rapid changes which are undergoing. We will then briefly understand about the architecture of DDR4 3DS memory which was employed for the verification. We will then understand the challenges which are faced by the present-day verification engineers and the motivation for using channel model for the verification of DDR5. The, the reference architecture used for verifying the DDR5 would be explained. We will then understand how the channel model was developed to make the silicon effects and how it helped in the verification of DDR5 supporting DDR4 CDS memory and gave us more confidence for the design verification. We will end the presentation with summary and future scope followed by Q&A. We are at a critical juncture of the VLSI design industry where new technologies like superscalar, quantum computing, carbon nanotubes, and spintronics are undergoing many improvements. The length of channel between the source and the drain, which defines the technology node, is decreasing over the years. As can be seen in the foundry roadmap of the different fabrication companies, the channel length has decreased from about 40 nanometers in the year 2015-16 to about 7 to 6 nanometers in the year 2019 to 20. And currently we have transistors as small as 4 nanometers. Active research is happening in designing even smaller transistors. With the decrease in the technology node, newer geometries have come up. The transistors have evolved from the classical planar FET to planar double gate to the FinFET. In FinFET, the gate wraps around the channel and source and drain acts as fin on the silicon surface. This later evolved to the tri-gate FinFET, where two or more fins are surrounded on three sides by the gate, and GAA FET, gate all around FET, a channel is surrounded by gate on all the sides. GAA transistors can be based on either nanowires or stacked nanosheets aligned either parallel or perpendicular to the substrate. The industry consensus has gradually converged on using horizontally stacked nanosheets as the best alternative for the 5 nanometer generation. These devices start with alternating layers of silicon and silicon germanium patterned into pillars. At sub 3 nanometer technology, active development is happening in designing vertically complementary FET, CFET, putting the NFET below the PFET in a standard cell. These devices depend on the junctionless devices with two complementing nanosheets separated by an oxide layer. Memory is an integral component of all the computation. In most cases, the memory is a bottleneck in the performance of the processors and has undergone many changes. Figure shows the DRAM roadmap of different companies, with Samsung being one of the world leaders. The JEDEC organization, which specifies the standards of DRAM, has defined and developed three DRAM categories of standards to meet power, performance, and area requirements for the target applications. These are namely standard DDR, mobile DDR, and graphics DDR. Standard DDR targets servers, cloud computing, networking, laptop, desktop, and consumer applications, allowing wider channel widths, higher densities, and different form factors. DDR4 has been the most popular standard in this category since the year 2013. DDR5 devices have recently been released. The mobile DDR targets the mobile and the automotive segments, which are very sensitive to area and power, offering narrower channel widths and several low-power operating states. The de facto standard today is the LPDDR4, with LPDDR5 devices recently released, and also LPDDR6 devices are expected to come in the future. Graphics DDR targets the data-intensive applications requiring a very high throughput, which are the graphics-related applications, data center acceleration, and artificial intelligence. Graphics DDR, GDDR, and the high bandwidth memory (HBM) are the standards in this category. Now, we will briefly understand about the architecture of DDR4 3DS memory, which was employed for the verification of DDR5. DDR4 3DS stands for Double Data Rate 4th Generation 3-dimensional stacked memory. In contrast to a stacked solution like the DDR4, The DDR4 consists of a redistribution layer which redistributes the signal to the different dies using the bonding wires and thus provides high loading. In contrast to this, a TSV solution like the DDR4 CDS, an etching technique is used to connect the master die, the bottommost die, with the slave dies, the other dies. The master chip is the only interface on the stack that communicates with the memory controller over the data buffer on an LRDIMM. The TSV is an effective solution for achieving more capacity in less unit volume without adding bus loading as compared to adding more packages or modems with more loading. It has improved turnaround time due to seamless writes and reads, higher bandwidth, and superior energy efficiency as compared to the multi-rank solutions. The structure of 3DS devices means that there's a potential for interstack operations to happen with less delay than the interrank operation. The different stacks in the DDR4 series are referred to as the logical ranks. The logical ranks are selected by the chip ID signal. Each logical rank contains many banks and bank groups. Because of this complex and closely knit memory architecture, even slight variation in the nature of signal can cause large concern. In the previous slides, we understood about how rapidly the VLSI industry is changing and the complex memory architectures. These factors present a lot of challenges to the present-day verification engineers. Since verification takes up a large part during the development of a chip, there's a need to produce low-cost and high-quality chips in order to meet the strict time-to-market constraints. Hence, the role of verification engineer becomes even more important. Thus, there are many challenges knocking the doors of the verification engineers. The verification environment need to be robust in order to cater to the evolving trends. There is a need to find bugs early in the design in order to avoid multiple respins. The strict time to market constraints mean that there is a requirement of high quality design for which high quality verification is a necessity. We need to adopt the latest verification practices and enhance one's knowledge base. In order to meet these challenges during the verification of DDR5, we have been motivated to develop an in-house channel model. A common memory subsystem consists of a memory controller and PHY which interacts with memory through the channel. The signals communicating over the channel are affected by factors like temperature and voltage fluctuations, noise, and symbol interference. These factors manifest in the form of skew, distortion, glitch, and crosstalk. In order to account for these factors, during the digital verification of DDR5, we have been motivated to use an in-house channel model. The in-house channel model is developed as a UVM-compliant model in a parameterized way. The commands which are sent by the memory controller are sent through the channel model to the memory. The memory behaves in a similar fashion and it routes the commands to the channel model, which is finally sent to the memory controller. Having a channel model enables us to find bugs during this communication early in the design, which would otherwise be possible only during the silicon validation stage. We now understand more about the channel model in the subsequent slides. Figure 8 shows the test bench architecture employed for the verification of DDR5. The memory controller MC uses the DFI protocol to interact with the PHY, which is the design and the test. In our case, we have used DFI 3.0 protocol. The PHY translates the DFI protocol to the memory protocol and sends it to the channel model. The channel model applies the user-defined disturbances and sends it to the DDR4 3DS memory. The DDR4 3DS memory in turn sends the command to the channel model, which finally reaches the PHY. The PHY translates the memory protocol to the DFI protocol and sends it to the memory controller. We have used the verification IPs for the DFI and DDR4 CDS components. Assertion checkers have been used to check the PHY functionality along with coverage monitor and scoreboarding. The channel model is used to model the silicon effects during the verification. It is developed as a standard UVC in a parameterized way. The different features supported by the channel model are generated the manifestation of the effects in the digital time domain by using common system verilog constructs like always, forever, and their assigned statements. The parameters are varied in accordance with the genetic timing parameters and the phi specification. Figure 8 shows a top-level diagram of the channel model with signal 1 as the input and signal 2 as the output. The channel model consists of multiple instances of the basic channel model element. Each channel model instance corresponds to one interface. There are 5 basic parameters which have to be supplied to the basic channel model element, which is the width of the interface signal, the number of ranks of the memory to which it is interfaced to, whether it is driven or received by the phi, and the feature that we want to enable. Figure 10 shows how the channel model behaves during the drive and the receive path. In the drive path, phi out is the output of the phi is given as the input to the channel model, and mem in is the output of the channel model which is given as the input to the memory. In the receive path, the mem out, which is the output of the memory, is given as the input to the channel model, with phi in as its output, which is connected to the phi. Figure 12 shows a bird's eye view of the different features which are supported by the channel model. It shows the input signal followed by an ideal output signal. In the case of ideal output, no channel model features have been enabled, and hence the input and the ideal output are equally same. Skew may be also introduced using the channel model. Here, a skewed output is shown, where there is a skew between the input and the output. Distortion can also be added on the input signal to decrease the valid window margin. Here, the distortion has been applied on the left and on the right edges where the signals change. The duty cycle of the signals can also be varied. In this case, the duty cycle of the output signal is less than the duty cycle of the input signal. Random glitches can also be added on the input signal in order to stress test the design. Now we will understand each of these channel model features in detail. When the output of one block is given as the input to the other block, skews may be introduced during the communication. Channel model can be used to model these skews. Figure 13 shows a case of an original signal followed by a skewed signal, which is a skewed or a delayed version of the original signal. This skew may be due to board delay, the DDR placement on the DIMM, or any other factor which you want to consider. The user can specify the absolute value of skew as well as the relative skew between two signals. Can specify the minimum and the maximum value within which the skew has to be varied. Distortion can occur on the signals due to noise and symbol interference. The channel model supports the feature of the distortion. As can be seen in the figure, the valid window margin, which is the range over which the signal is valid, is decreased by the left window distortion and right window distortion. The user can specify the nature of distortion to be applied, which can be X, Z, 1, or 0. The user can specify the absolute value of the left window distortion or the right window distortion, or can specify a min and a max value within which the distortion has to be varied randomly. Crosstalk can also be simulated using the channel model in order to simulate the capacitive and the inductive interaction between the neighboring wires. In our proposed channel model, the crosstalk is based on the capacitance coupling model. The crosstalk model takes the I/O signals having the different values as the input in order to generate the I/O noise. The crosstalk model compares the value of each bit in a bus to the bits in its neighbors, and if the value is opposite, the score is increased by 1. In our case, we have only considered the effect of crosstalk due to two neighbors. However, there is a user configurability to increase or decrease the number of neighbors to be considered for the crosstalk. Let us consider the crosstalk for the bus having these following values. In order to calculate the crosstalk for the bit phi, we will compare the value of bit phi, the value of bit 3, bit 4, bit 6, and bit 7. The value of bit 7 is opposite to the value of bit 5. The score is increased by 1. This score is multiplied by scaling factor, which can be supplied by the user in order to generate a dynamic noise of about 5 picoseconds. The duty cycle of the signals can also be varied using the channel model by varying the off and the on states. As can be seen in the figure 50, the duty cycle of the original signal is about 50%. The duty cycle has been varied in the duty distorted signal. The duty cycle is initially less than 50% and later more than 50%. The user can specify the exact value of the duty cycle which he wants to give, or can specify a minimum and a maximum duty cycle within which the duty cycle has to be varied. Random bridges can also be introduced on the signals which can occur due to temperature or voltage fluctuations. These bridges help in the stress test of the DUT. As can be seen in the figure, random bridges have been applied on the input signal. The user can specify the number of bridges to be supplied in a unit interval. He can also specify the duration of each glitch. Till now, we have understood the different channel model features. Now we will understand how the channel model helps in the verification of DDR5 supporting DDR4 TDS memory. Figure 16 shows the top-level interface connections between DDR5 and DDR4 TDS memory. It shows the clock signal CKT and its complement CKC. The clock enabled signal CKE and the online termination is also shown. C0 to C2 represents the chip ID signal which is used to select the different logical ranks in the DDR4 TDS memory. CSN is a chip select signal which is used to select the different ranks. Activate row understroke, column understroke, bank group, bank address, and the address signals A0 to A17 are shown. These are input to the memory from the file. In addition to this, the data signal is represented by the DQ, which is sampled by the store signal, which is the DQS. Data mask, data bus inversion, TDQS are also shown. Priority alertn and resettn are also some of the other important interface signals between the DDR5 and DDR4 TDS memory. The different features supported by the channel model can be applied to each of these interface lines independently. There is a user configurability to apply skew, distortion, glitch, or crosstalk in a rank-wise or in a random fashion. We can change the value of each of these parameters at runtime. For the purpose of illustration, we will use DQ and apply all the channel model features supported by it and see how it was beneficial during the verification. The data integrity is ensured by the alignment of DQ and the DQS. Read and the write training algorithms are performed in order to achieve a maximum window for the data add. In the following slides, you will see some of the snapshots which were taken while the read and the write training algorithms were performed. Figure 17 shows a scenario where a skew has been added on the DQ lines. It shows the clock signal followed by the DQ idle signal. The DQ idle signal is the input to the channel model, and the DQ skewed signal is the output of the channel model. As can be seen, there is a skew between the DQ ideal and the DQ skewed signal. This skew is expected to be compensated during the read and the write training algorithms. The duty cycle of the DQ lines can also be varied, as can be seen in figure 18. The duty cycle can be varied to change divided window margin. It shows a clock signal followed by the stroke signal, which is the DQS. The DQ ideal signal has a 50% duty cycle. The duty cycle has been varied in the DQ to be distorted. As can be seen, the duty cycle of symbol D1 has been increased by 20%, and the duty cycle of symbol D2 has been decreased by 20%. Distortion can also be applied on the DQ lines. As can be seen in the figure, it shows the clock, the DQ ideal signal, which is the input to the channel model, which does not have any distortion. The DQ distorted signal is shown, which has a distortion of X on the left and on the right edges when the signal changes. Below is a magnified version of the above figure. Here we can clearly see that the divided window is decreased by the left window distortion and the right window distortion. Hence, we can see that having a channel model helps thoroughly verify the 5 features. We found that even after following the setup and the hold time, the addition of skew and the distortion brought forth many issues which would otherwise be detected only when the silicon was out. He caught many issues during the read and the write training algorithms, where the design was not able to compensate the skew and the distortion which were added by the channel model. Hence, the addition of channel model in the verification environment improved our design verification quality, summary, and future scope. In this presentation, we understood about how rapidly the VLSI industry is undergoing many changes and the newer memory architectures are coming up. We exposed many challenges that present-day verification engineers have to have a commensurate improvement in the design verification practices as well. We then understood the motivation for using channel model for the verification of DDR5 supporting DDR4 TDS memory. The test bench architecture used for verifying the DDR5 was explained. We then saw how the in-house channel model was used to mimic the silicon effects during the verification along with the different features supported by it. We then understood how the DDR5 supporting DDR4 TDS memory was verified in a robust fashion with an example of TQ. Thus, the channel model enabled us to find bugs early in the design and also to test the DUT. The channel model is developed as a generic block. It can be used to verify other designs as well, which involve the communication between two different IPs. The proposed channel model is a very basic one and has a lot of scope for improvement. Channel model can be modeled using the real number modeling and use frequency domain as well. X models can be used for characterizing the analog behavior in the digital time domain. Factors like variable voltage, channel losses, attenuation, and impedances can also be considered in the channel model in order to create a mixed signal kind of environment. I would like to thank DVCon for giving us the opportunity for presenting our paper. I would also like to thank the panelists and the participants for attending the presentation. Last but not the least, I would like to thank Samsung Semiconductor India R&D and all my co-authors and colleagues for making it happen. Thank you.
Okay, Aditya, thanks for your presentation. Again, if you have any questions, please feel free to add them to the chat window, chat box. And maybe I'll start with a question, Aditya. You're talking about this channel model features. How do you compare these features or the things that you implement there to the real life situations? How do you know that these are proper features?
Actually, by using the channel model, we are trying to create a real-time environment during the verification. Basically, in order to vary all these parameters, we have these parameters have been varied in accordance to the memory parameters, the JEDEC parameters, as well as the PHY specifications. So the designers give us the range within which the skew and the damage can be varied, which is supported by the PHY. So using the channel model, we are able to exercise all these factors during the digital verification.
Okay, thank you. Any other questions? Okay, if not, then again, Aditya, thank you for your presentation. And let's now wait a couple of minutes before we start with the next one. Thank you.
Good morning, everyone.
Good morning,
hello.
Mehmet. We can hear you.
All right.
Thank you. Okay, let
so-
me start, Mehmet, by introducing you. So good morning, everybody. See, we have a few new participants in this session. So again, welcome to DVCon 2021. As in previous sessions, of course, please feel free to enter your questions during the presentation in the chat box. After the session, we have a few minutes for questions. And of course, also don't forget to vote for the best paper award. So the next speaker is Mohammed Tukel. I hope I pronounce this correctly.
Yeah, that's correct.
Okay. Mohammed holds a bachelor and master degree, the last one from the Istanbul Technical University. See, Mohammed, that you've been working in various domains like digital design, software development, as well as design verification over the last 14 years, so a lot of experience there. And the last 6 years, you were working as a design verification lead. The title of your talk is about using dependency injection design patterns in power-aware test cases. So thanks, Mohammed, and the floor is yours.
Thanks for the introduction, Roger. Sorry. Okay. So, yeah. Okay. So, am I sharing the current screen? Is that?
Yes, we see the title and now the agenda. Okay, thank you.
Okay. So, very good. So let me go one slide back. Yeah, so the title of the presentation is Using Dependency Injection Design Pattern in Power-Aware Tests. So as most of you know, dependency injection is not new. So it's a known design pattern. So today I'm presenting, you know, sometimes you see an example code, an example methodology, and then you say, yeah, I wish I knew this before starting this project. So the methodology we are presenting here is kind of like that, you know. So it's good code practice and it enables you and it solves some of your problems. So agenda is I'll talk about problem statement and goal. So what are we trying to achieve here? And possible solutions, what can be other solutions if you have a power-aware test bench and you want to use systematic tests that are extended from one another. So our preferred solution, and then I'll give a system verilog example, system verilog UVM example for the methodology we are describing, and a case study, and then an example test. So these are system verilog UVM examples, just to show you a live example and how it works. And then I'll summarize my talk. So problem statement. Yeah, so if you keep a test base for your project, you know, and if you think one test base class is okay to develop all kinds of functions, tasks, and the things you need, so then it tends to become too large, you know, a few thousand lines of code, and it would become hard to maintain. And so when you deliver it to somebody, when you hand over this code to somebody, it'll be hard to read. And then for new starters, it would be hard to understand, and it takes a lot of time to ramp up. So also versioning tools, you know, it's not good to have large files for versioning tools. It might give you headaches and merge conflicts. So most of the teams now have multiple people, so everybody delivers their code, and then you often might have merge conflicts, and for larger files, it's even more painful. So our goal is so to keep the lines of code shorter is preferable. So our goal is have multiple hierarchical test base classes. So instead of one test base, we can have multiple hierarchical test bases. So just to decrease the number of lines of code and give a more readable code base. So separating the test base based on clock reset, building, VIPs, power aware functions, and etc. So it is good practice. You can separate encapsulate the different functionalities in different test bases. It'll help people understand where to look at, what to implement, what to use. So in their test cases, right? So except the power dependency, encapsulation of the rest of the features of test space are relatively straightforward. So what I mean is, I'll show in a diagram. Yeah. So as you see here, if you use UVM library, so you extend your test from the UVM test and then base test and then utility base test. So this is an example, and you might have many tests in between, and at the end you have your test cases. So this is the concrete test case that extends from all the way through UVM test. So how do we add the power aware test? How does power aware fits in this diagram? Okay. So our possible solutions are, so you might have a completely different test bench for power aware tests. Okay, so this is one approach, and if your focus is power verification and it's mostly integration, and if you don't have multiple whips, that sort of verification is done in another level. So then you might choose to use this. The obvious cons are you have to maintain different test benches for power aware and non-power aware verification. So obviously it can only work in certain test benches. So you can make every test power aware. So obviously this is a straightforward approach, but then all power aware features will be available to all tests. And if you run them all power aware, you have bad simulation runtimes, right? So your simulation runtimes increase. So extending the test case from different parent tests. So you can have a power aware and non-power aware based test. You can do that. So basically, you would run the power aware with a slower runtimes, right? The test bench that has all UPF annotation and etc. all the models. So the cons are, if you choose this, you know the parents and the test cases become tightly coupled, and then it's very hard to move a power aware test to a non-power aware test or vice versa. So, and there are a lot of if-thefs floating around if you choose this, and because you have to guard some power aware features in initialization and other places. Yeah, so if you choose to have two base tests, and if you want to make IP base tests, so suppose CPU test space for verification of different sub IPs in your DUT. So you can have different base tests to rep some kind of common functionalities for certain tests, right? So it can have same initialization or whatever. So in that case, then you have to extend from power aware and non-power aware. So you have to duplicate your base test. So another approach is similar to this one is you can have it again a single base test, but you can make it power aware and non-power aware the same test by using if-defs and so preprocessor macros. Using preprocessor macros, so you compile it one way, it becomes a non-power aware, and you compile it the other way, and it becomes power aware. So everything can be guarded by if-defs or things like that. So again, it becomes hard to maintain, and it becomes hard to read due to obvious reasons, you know. So at what times you need power aware and non-power aware features, they just become very mixed up, you know. So yeah, the last one is dependency injection that we are proposing here. So there's no runtime impact. So the power aware simulations on the power aware test run on power aware test bench, which means you have UPF elaborated and models are in place. So same base test can be used for power aware and non-power aware. So it reduces to keep different sorts of base tests. Promoting a non-power aware to power aware or vice versa is a lot easier than the other implementations, and obviously it improves reusability and scalability, and of course encapsulation. So in our opinion, there is no downside to this approach. So how does it play in this diagram? So as you see, as I said in the beginning of the presentation, the dependency injection is not something new. So it's a known design pattern. It's basically a composition. So we are adding the project specific test base, the base test that is the parent of our concrete test cases. So we add this component into this test space. So it injects this test base injects the power component, which gives us our power aware features, you know, power down, power up, whatever you need. So all those features, so dependencies, however you like, tasks. So it gives all these functions. And then a non-power aware test should instantiate a blank or base power component, which has a minimal implementation. You know, the only implementation that's valid in a non-power aware test. So, and the power aware version of the test, you can have a flag, a bit that is set, you know, and then you can define whether a test is power aware or not. So you can also pass this argument from command line. So however you use in your test bench. So the power aware test can instantiate the concrete power component. So therefore, due to polymorphism, power component methods should work based on the type of the real instance. So a power aware test, the initial bring up, initial boot up, power up, whatever you call it, behaves differently. It calls supply on calls, you know, it does, if there's any power sequence, it can do that. All sorts of different sequences you can implement. And in a non-power aware test, it just does the minimal operations. So here I have a small power component system Verilog example. So on the left-hand side, I have power component base and power component classes. On the right-hand side, I have the project test base that instantiates these. So as you see, I have defined power up and power down tasks. So in the first power base class, power component base class, they are blank. So as I said, they are the minimal. They have the minimal implementation. So in power component concrete class, so I have real implementation. So I have supply on calls, supply of calls, power sequences, depending on your duty, whatever you need for your duty. So here the test base instantiates the power component based on whether the test is a power aware test. So this can be, as I said, from by other. So it can be set from a command line or by something else. So and then when you run in run phase, if you run power up, so if the test is power aware, it does just the right sequences. If it is not a power aware, it does whatever you put in the base component. So you don't need to worry about if this is a power aware test and you need to guard here and there. So you don't need to worry about that. So all the tests work like look like a power aware test, but inside you can define whatever you want. So this is the beauty here. Yeah. So I just want to show what kind of, designs or what is possible, just to give an idea. So for instance, you might have a design that has two power domains, and in first power domain 1 and power domain 2, you might have retained logic, and then you might have a power switch. Even you can have this kind of I'd say advanced power structures. It is you can do this. Yeah. So suppose you have such a design, and then you want to test function 1, right? So that function 1 can be any future. Suppose it's an AHP transaction, an AXI transaction, an AHP slave, or AXI slave. You want to test that future. So you can implement check function F1, so which can be also a non-power aware future. So you can implement your test in such a way that it does multiple times of this testing, just for robustness. And you can power down your domains in order. So it depends on your duty. And then you can stay in low power mode for some time, and you can power restore for some time. You power restore your domains and then do this in a loop. So say 5 times. So if you write a test like this, and then if you keep power downs and restores with minimal configuration or blank tests, so what you have is you run function F1 multiple times. So you can use this test. This is a power aware test, right? So you can use this power aware test in a non-power aware environment. In a test list, or however you use your test suite. So you can use the exact same system Verilog code as a non-power aware test, and you shouldn't need to change a single line of code. So this is just an example. You don't need to use the power aware test as a non-power aware test, obviously, but I'm showing here that this is possible. So, and the initial power up, right? So there's also a lot of things going up here. So, and you don't need to, a usual test case doesn't need to worry about what's happening here. if it is a power test or non-power test, it doesn't, the user developer doesn't care. So, and most importantly, it gives you a great opportunity for maintenance. Yeah. So I'd like to summarize my my talk here. So first of all, encapsulation of the PA dependencies, tasks, futures, however you like, into a separate class component. So this is, I mean, I have seen great benefit of this of the encapsulation of power aware futures. So mainly, so it is, even though many people are using power aware test benches, it is still not the same. It's not at the same level, you know, like other verification tools or ideas, or so it is still. So if you hire someone, new, or if you give this task to someone who hasn't done power aware verification before, so he or she just needs to understand that component, and everything is perfectly in place. And then if something is need to be modified in a different project, they just need to update that class or those classes. So it is, I mean, it looks like most of the time people don't pay enough attention to how to implement the code, but encapsulation is, I think, one of the most important items of this approach. So it gives you a good level of encapsulation for power dependencies. Yeah, so as I said, it is not that easy to separate power, because you have to have initial power up, and it is just it is not that separate, because in reality, in the real silicon, the chip works as a power aware test, right? So everything is power aware, but we want to make separate test groups, because we don't want to run all the tests in power aware setup, because they run slower, right? So and considering a smaller piece of our tests are power aware, so it's not good to run everything in a power aware setup. Yeah, as I said, having a separate component for power aware verification is giving a lot of. So I mean, if you are a team leader, you have to consider these things, and if you develop a code like I explained here, you can give it to someone, and then they can quickly ramp up. So reducing the number of lines of code helps solving our merge conflict problems, and it saves you, I mean, half an hour a day. So if you have multiple people in your team and delivering into the same code base, it also helps you there. Yeah, improve scalability and reusability. So as I said, you don't need to maintain two different test benches or two different base tests. So it increases scalability, and then you can quickly reuse the power component if you have the same kind of power aware features in different projects. So which is usually the case. So reusability is increased. Yeah. By using the proposed approach, a non-power aware test can be promoted to power aware test and vice versa without needing to edit the code. So for gate level simulations and power aware gate level simulations, to keep the same list of tests for your gate level simulations is very helpful, and you just need to maintain those set of tests for your gate level simulations, right? So overall, this method helps reducing the verification NRE. So yeah, I'm finished, and thank you. I can take your questions now.
Okay, thank you, Mohammed. So if you have questions, please feel free to enter them in the chat box. Maybe let me start by asking one question. So if maybe you can go to the slide where you have this UVM component.
Here?
Oh, sorry, the test case where you, yeah, this one.
Yeah.
Yeah, so let's say from a development cycle point of view, I think at least my experience is that typically let's say the non-power aware test cases are developed earlier than the power aware test cases, right? Power aware simulations typically something you do later. So,
true, yeah.
So do you have also experience in that let's say the test case that you're in one of the other slides, you have the test case that is that you can run both power aware and power unaware, that it is typically that you use a test case, maybe extend the test case, an existing test case that was running non-power aware and make that power aware. Is that?
Yeah, so that's actually a very good question. So I tried to explain it here, but in a short time, so I probably wasn't that successful. So so your point is very good. So we all know that we start gradually, right? So we start developing our test bench gradually, and the first test, the main functions of the DUT. So suppose function F1 is one of the functions that has the DUT, and I'm validating it by this task. So I can develop a test like this, and then put here these calls, and the power component base is basically empty. I mean, you can have an empty power component base, and then you can have these tasks empty with blank or with just UVM info, and then you can have this test as your initial test. You know, you can have you can validate function F1, and these calls would be just UVM infos, and then you can gradually develop your power component, the concrete power component. And if you think it is done, you have finished your power component, you can run this in a power aware setup, right? Where you have UPF1 notation, and then all your power models and everything. So this is what you can use if you want to keep the same tests for power aware, non-power aware, at least a certain amount of tests. You can do this.
Yes. Okay. Thank you, Mohammed.
Yeah,
any other questions from the audience? Okay, if that's not the case, once more, thank you, Mohammed, for your presentation. And
yeah, thanks everyone for joining. All right, thank you. Bye now.
Bye.